not in, for some reason. It's almost as though they were big sporting events, and I swear like half my students were either hungover or exhausted, but more likely a combination of both of those things. But that's what happens when, your team wins the Super Bowl. And being a native Atlantan, I was very happy to see that Bird team beat the Patriots after, Patriots beat my Bird team. So, go Bird teams. All right, so today we are going to go over the linked lists. But first, I just want to make some announcements. First, there's job fair stuff going on. And now you should be all getting announcements from Rose, right? Right. I just want to remind you, there's a speed job fair on Wednesday. Bring your resumes and stuff, and go and go to the job fair on this Friday. Now, you may not think that basically you might not be skilled enough or something like that, or you don't have enough experience. And what I'm telling you is by the end of this class, you should be, because right now you're going to be able to, once, let's say after this lecture, after tonight, you should, and especially after our upcoming exam, which I will tell you about in just a second, you should hopefully know enough to answer some of the interview questions that they would ask about linked lists, which are a fun topic that gets asked for interview questions. So now that I've said that horrifying word exam, let me go ahead and start talking about that. So the objective is that basically our first exam, I am still hoping for it to be on this upcoming, not this upcoming Friday, but the Friday afterwards, or Thursday afterwards for you guys, right? Whenever your lab is, not this week, but next week. So that would be, let's open up the calendar. We're aiming for the 15th for your exam. Now, that being said, this whole thing about the labs being canceled on the 8th, right, that might give me pause, and I might push it back to the 22nd, but it will be either on the 15th or the 22nd, and you will know, and I'll have a decision forthcoming. And part of that is because basically everything that I want to cover everything I would want to cover on the exam, we should be done with tonight. Now, of course, if I don't get done with that, then I'll most likely push it back to the 22nd. That being said, the way this exam will work is that it will differ from the exams I've given in previous semesters. So the more resourceful of you probably have friends who have taken this class, and I give back my exam, so you probably would have the opportunity to see them. Now, that being said, I'm going to be changing this exam around this semester. So the first exam I've normally made completely closed, no notes, no anything. This one I think I'll allow you a cheat sheet, and I will tell you one question in advance, okay? And I'll tell it right now what one question will be, and it's worth 20 points. It will also be on the practice exam, which is that I want you to compare and contrast the various features of array lists versus linked lists. We'll go over this in class in good detail, but this is worth 20 points. Now, on the practice exam, which I'll talk about in just a second, I just simply give you that prompt, compare and contrast them. On the actual exam, I'll tell you compare feature X, feature Y, and feature Z. Okay, so you'll have a bit more guidance on the actual exam. Okay, so now let's talk about the practice exam and why it's an awesome thing. The practice exam, I typically create those by generating twice as many questions I need for an exam, and then giving half of those questions to you, and then I keep the other half for the actual exam. So the practice exam, I normally try to make a bit tougher than the actual exam. So if you can do well on the practice exam in the time limit that you would have, then you'll do well on the other exam. I also try to make them so that you could probably complete them in the normal lecture time period, which is an hour and a half, but we take them in lab. So the seats are going to be a bit weird because you're going to have to figure out your best to get around those keyboards, but you'll come up with something, I'm sure. The exam, you'll get the whole hour and you'll get the whole lab period. So our exams take place in the lab rather than in this lecture. Okay, that makes sense to everybody? So, and you will get that practice exam at least a week beforehand, and I will, if I don't post answers, then at the very least I will post an answer video. Okay, so that's upcoming exam. So next we are also going I'll be probably posting this tonight, but you will be getting a homework tonight called which will be solving the Josephus problem. Now, this is traditionally where basically students start saying the homework becomes hard. And this is only because basically you just got to really think about memory locations and that stuff. Like basically you've got to understand the whole, let's see, I've got examples here, like how the add method actually works. You know, what the temp.next equals head and then head equals temp, what actually goes on in those lines. And so as long as you're following the lectures, it shouldn't be too hard for you to do this assignment, okay? It's just, it feels bigger than it actually is. It's not actually a big assignment, but it feels big, if that makes any sense. Because all you're going to be doing is implementing the add method, the remove method, and the get node method. Those are the only things you have to implement in that, and then you have to use those to solve the Josephus problem. But you'll see how that works out. So this is basically around the time where I'd say the difficulty of the course peaks, right? It doesn't necessarily get any easier, but it's not going to feel any harder after this, is the idea, right? All the other problems, and this is also because the problems over here aren't make work problems anymore, right? The first 3 weeks were like make work problems. After this problem, we try to work on basically interesting projects. So like the Josephus problem is an interesting math problem that needs to be that's actually very interesting to solve, and it's actually an interesting scenario, and it's interesting to think about. We'll be using when we go into recursion, we're going to be trying to do stuff like we'll solve the problem that's been given as homework for basically the past 50 years, which is the 8 queens problem. But we're also going to learn how to do Sudoku and how to solve basically any Sudoku puzzle we get tossed. So stuff like that. We're going to basically be working with a lot more interesting problems from here on out. So while it does become a bit more difficult just because the problems look bigger, it's not necessarily more difficult. It's just going to feel that way. So that being said, these next 2 weeks are basically where if we're going to tell you to focus, to have time to focus on, if we're going to tell you to focus on my class at any given time, it'd say this week and the next week, would be the time to focus on my class. All right, so let's go ahead and resume where we were. So we were talking about linked lists, and we were doing and remember, a linked list is just kind of this weird scavenger hunt through our program, right? We've got our private class here, node, which basically is very short, and the nodes are not Russian nesting dolls, right? Even though it's got a node here and a node here, it's not that you have a node inside a node. This says that this is the memory location of the next node. This stores the memory location of the next node, so that basically whenever you call .next, it brings you to the next node. Okay, and what these nodes do is that they store both the item and the next node. Okay, and what we found out is that we can do some interesting things, like we can use this statement over here, set head is equal to current, and then use current equal current.next to advance current to be, if we call this once, it will be the node after current. And then if we call this again, it will be the node after that, because we resolve this memory location and store it in here, right? So basically this line sets it up to head, then it's the node after head, and then it's the node after that, and then the node after that. So we can iterate through a linked list using this. Now generally, and I'll mention this like a lot when we're solving some of the problems on the practice exam and on the actual exam, generally unless you're writing a method inside a linked list, you don't really get the chance to use the next node. You don't get to use the next pointers. Unless you actually have access to the node class by being inside the linked list class, you don't get access to the node and the next, because next is private, so there are no nexts. So most of the time, if I give you a problem and I give you nodes, then it's a good idea that you're probably going to have to use next pointers. Otherwise, or if it's inside a linked list class, you'll have to use next pointers. Otherwise, you treat it like any other list. All right, so where we left off was the add method, and we said we wanted to add an item at some index, and we set up 3 conditions. The first condition was that basically making sure that this index was not out of bounds, right? It was an index we could actually add something to. Okay, and I'm going to keep this in line with the other class. Then I created a node I called adding, which is the node I'm going to add to the linked list, right? Okay. If the index was equal to 0, I was adding a I was adding a new node to the head of the linked list, right? That makes sense to everybody? So I was saying, so let's go ahead and walk through this. I just want to review this because I feel like it's worthwhile to review. Whoops. What we would do is that if the index was 0 and we've got a linked list over here, and this node is currently the head, and we've got other nodes after this, right? And we want to add this node over here. So this is head, right? And this is the adding node, or the node that we're adding to the linked list. The first line that we do is that we said adding.next is equal to head. And what this does is that you can read it as we're attaching adding the head using the .next pointer. Or we are storing head, the memory location of head, in addings.next variable. But abstractly, it looks like that. Okay? That makes sense to everybody? This is refreshing all your memory, hopefully. Right? Then the next thing we do is we store adding in head. And what that is that actually, remember, head is over that head label over there. That's a variable, right? Somewhere else, right? This is a variable somewhere else called head. And right now, it's storing the memory location of this node. And what we're saying is that actually in head, we should store adding because it is the new head of the list, right? That makes sense to everybody? And similarly, this adding has something pointing to it as well. But this node is now adding and is the head. Okay. What about the other thing? What about the other condition, right? We have basically if the index is 0, else everything else, right? Well, otherwise, if we want to say we've got this scenario over here, right? Else, let me scroll down. So our code says otherwise, adding. Yeah, sorry for changing the wording on you, but I'm just making it consistent with the other classes. So we've got our head node over here, and we've got actually I'll switch this up. Right? What if we're adding it to any other index, right? Say we want to add this add this item to index I, right? So let these nodes be I plus 1, I minus 1, right? Okay? And then we've got plenty of nodes, before and plenty of nodes afterwards, right? So the idea is I want to add this guy, this adding node, which I've created, somewhere in between here. Now I can't just grab this node over here and just attach it like this because this doesn't anything. I also have to adjust the list. So what I do is that I grab the node before where I want to add, not the node at index I, because if I grab that node, there's no way I can manipulate this pointer, right? So I have to grab this one so I can manipulate this arrow. So I grab him as before, and I call this node before. I label him as before. And now I can say that this is the line that most people get confused with. Before.next gets stored in adding.next. So basically I'm saying point adding to whatever before is pointing to, right? Before.next, this is the memory that gets you this memory location. We're storing it in here. So now this points to this guy. Okay, and now we say adding, the memory location here, gets stored in before's.next pointer. Which updates this to be over here. And now this one, of course, becomes I. This is now I plus 1. And this is I plus 2. That makes sense to everybody? Unfortunately, that was caught in the small screen, but that's fine. Then we increment the size. So let's go ahead and do a big O analysis of this. Right? This is a constant time. Just check to figure out what's going on here. Making sure if it's too small, right? If it's too small or too large of an index, we just throw it out. If it's the first thing in the list, this is just changing up pointers. These are constant time operations over here, right? And these two operations over here are constant time operations here. They're just changing memory locations. But this over here, the get node operation, that uses a loop to go through the entire, to find, we have to iterate to the actual node in the array, in the linked list. In an array list, we could just instantly go there, right? Because we know what memory location to look at. But here we actually have to go through the entire scavenger hunt to find the node we want to get to. So this get node operation is O of n. So adding anywhere else but the first location took O of n time. Now most linked lists, and we'll do this at the end, most linked lists, they also have a tail pointer as well. So we can add to the tail in constant time as well. Right now, just to keep things simple while we're doing this, we're going to just use a head, because that's all technically you need. But having a tail means that we can add to the tail in constant time. And that's actually pretty good, even though adding to the middle, that's not so hot. If we store a location in the middle somehow, then we can we can just insert in the middle at that spot as often as we want in constant time. So that's one cool thing we can do. And the other thing is that most of the time when you add something, it's going to be at the beginning of the list or at the end of the list. So if you have a pointer to both of those, most of the addition operations will come in constant time. So that was adding. We also need to write a second add method, right, which is the public Boolean add method. Public Boolean add item, right, just adding an item onto the end of the list. And all we do to that is we call this dot add. The item at index size, and then return true, because that's not going to fail, right? That's all we have to do. We're just simply, if we're adding it to the end of the list, we just add it to index size. Make sense to everybody? Cool. So that other add operation just is going to call the other one. So let's go ahead and get started on the remove operation, which is the first actual new thing that we've got going on. So I had announcements at the beginning of class about like exams, which will be soonest on Thursday. It's Thursday next week, so be sure to take a look at the video once I post it. So, okay. So let's go over the remove operation. So public remove takes in an index, and it will remove the node at that index. So public right? Okay, it's going to remove the node at that index. So let's go ahead and just set this up. First thing, if we're removing stuff, definitely want to decrement the size, right? Removing something, okay? Next thing we want to do is that if we want to return whatever was stored there. So let's just go ahead and set that up. We'll have an to return, right? This is the thing we're going to return, and we'll just set it up to null because we have to initialize it if we want to return it, and then we'll return it down here, okay? And actually, as it turns out, the reason I program my linked list like this is because they're completely symmetrical. They will be completely symmetrical, which is that same three cases will apply, which is we check for if they're out of bounds, we're going to check if we're removing the head, and then we're going to check if we're moving anywhere else. And then when we add the other two ones, we will figure that out. I'll go into how we add a tail in the doubly linked list. For this one, I'm actually going to leave it as an exercise, which we'll be doing for your homework in a circular linked list. So, but I'll go over how we add how it works with the tail, okay, in a doubly linked list. Okay, so remove. So here we're going to remove something at a particular index. Okay, so let's go ahead through the first case because that doesn't actually require us to do much work, which is checking to make sure the index is out of bounds. If the index is less than 0, it's out of bounds. Or if the index is greater than or equal to size, in this case, it's going to be out of bounds. So remember, it's greater than, less than, and greater than over here. Its index is greater than size over here because you can always add to index size, right? And that makes sense because you want to be able to add to an empty list, right? Right? The first thing you're going to add to is index 0. And if you can't add with a size of 0, right, which would be the case, right, you couldn't add now to an empty list. You couldn't initialize your list if that was equal sign was there. But here, you can't remove an index that doesn't exist because the indices are 0 through size minus 1. Right? It's the same thing. It's the same logic over here for linked lists as it is for array lists. Okay? So we're just going to throw new index out of bounds exception. Okay. So now we have 2 more cases to do. Anybody want to remind me what those cases are? Right? If so, what's one way to translate that? How could I put that in terms of index?
Equals 0.
Yeah, exactly. The index is equal to 0. And the other condition is everything else, right? So, okay. So let's go ahead and draw these things. Okay. Let's go to the board and draw for a second. So removing the head isn't too bad, actually, it turns out. Removing the head is actually kind of trivial. It's one of the easiest operations to do for a linked list. So we've got our node, so this is our head, right, over here. And then we've got another node over here, the node that comes after head, right? And there's just a bunch of nodes that follow it, right? So what we need to do is we've got to store some, first thing we're going to do is because we want to return an item, we'll take the data and save it from head, right? So that's just one line. We just simply go, okay, to return is equal to head.item, right? That stores it. And so now when we return, we'll be able to return it here. Okay? Now, when it comes to removing the thing, all we need to do actually is make this location not store the first node, but the node after it, right? We have to store this node instead, right? If we remove this node, right, then this node will become the new head, right? That makes sense to everybody? If we remove this node will be the new head, right? Well, how do we remove something? How do we delete it? Well, it turns out that Java makes that ridiculously easy. What it's going to do is that it's going to count the number of objects that are, or the number of references there are to this object. And when nothing is keeping track of this thing anymore, right, the only thing that was keeping track of it was head, it's going to get marked for garbage collection and deleted. So all we have to do is store the location of the next item in head. So we're going to store inside head the location of the next item. So how do I get the item that's after the current head? The head we're trying to remove. Head.next. So head.next is equal to head. So we're going to take the current we're going to take the item, the memory location of the node after head, and we're going to store it in head, making that item the new head. That makes sense to everybody? So we just kind of advance head by 1, right? It's just like that current is equal to current.next over there. So now this gets marked for garbage deletion, and it gets eaten up. Okay? Yes?
Didn't we want to remove that one?
We only wanted to remove the first node. So this is the pointer for head. This is the pointer. This is storing it.
Oh,
right?
Okay.
So the other way to analyze this was the way to draw this is that I was using. Right. Some students find that easier if I rather than storing the node, I store the location here. But I like to move away from that pretty soon. So what I did is that I simply said we want to remove this item, we stored it, and then we said head is equal to head.next.
Right.
Right. So that was what that node on top was. It was storing the memory location. It was using it to represent the memory location of the top item. Okay. Now, otherwise, what if we want to remove all the other something else in the middle? Okay. Again, let's draw that out. So we want to remove something in the middle. So let's go ahead and do similar to what we were doing for adding in the middle, which is that we'll have I minus 1. We want to remove the guy at index I. And we want to remove the guy at, basically we just want to remove the guy at index I. Okay? So this is where basically it's going to get fun and interesting, and you'll see why people love using these to ask questions. Okay? So we want to remove this node, the ith node. Okay? Now, and we also want to do it in the most efficient manner as possible, but for right now, we'll do it a bit inefficiently, and we'll move up to, and we'll get to the efficient part. So if it's anything like the add method, then the first thing we want to do is we want to grab this node and label it as before. right? So that we can manipulate this pointer. Now remember, all we have to do to get rid of this guy is to make sure that nobody's currently pointing to him. So the way I'll do that is I'll take this pointer and move it over here, right? That's all I have to do, okay? So what I'll do to do that is I'll just call him toRemove, okay? And this will, so I'm going to do this once verbosely, and then I'm going to do it concisely, okay? Which is also going to be a bit verbose, but you'll see what I mean. Okay, so node E, so let's go ahead and get the before node. Before is equal to get node. So it gets the node at index -1. It gets the node before the one we want to delete. And this isn't going to fail because we know that the only way this statement would fail is if index -1 would give us a negative index. And that can't happen because of the way the conditionals are set up. Okay. Node E toRemove, the node that we're removing, right? It doesn't matter that we're going to label it, right? It will get deleted at the end of this curly brace because, you know, once this curly brace goes away, the toRemove goes away. Sorry, once the curly brace ends this else statement, the toRemove will go away. So get node at index, and this won't fail because index is a valid index, so that's great. Okay, so what we have to do now is save the item at toRemove. So toReturn is toRemove.item, right? That makes sense to everybody? So we're storing the item we're removing, we're storing its item. Okay? And now we actually have to adjust the pointer, right? We have to make before point to the node at I+1. So that means we have to change before.next pointer, right? And we'll set it to the node that occurs after toRemove, right? The toRemove is the one at I, so we'll set it to the one after there. Before.next points to toRemove.next, right? Make sense? Now, okay, so that's the verbose way to do that because technically, just like when we did the add method, we didn't need to get this node over here. We didn't need to get this after node is over here, right? We have two get node statements. Each of these take O of n time to do. So this entire statement would be 2 of n, which is still O of n time, but you know, we might as well make this as efficient as possible. So now we're going to remove toRemove and see what we can do if we can do this without toRemove. All right, remember, toRemove is technically, actually, let's go ahead and we'll slim this down first. toRemove, right? We don't need to actually do another get node operation to get it. It's just simply the node right after before. So this one would technically be before.next, right? So now let's see. So now that we have that set up, let's do this without using toRemove because most of the time you're not going to use it. Okay. So toRemove is equal to toReturn. The item that we want to save is located in the node that's after before, right? So it's the item in the node after before. That makes sense to everybody? So we go before dot next. So this resolves to a node, right? This is a node. And then we look for the item in there. That makes sense to everybody? All right, what about this one? Before dot next, we need to set this pointer to point to this node over here. So how can we do that? What is toRemove? To returns an item, so it wouldn't give us anything. So what was toRemove before I commented out? It was before.next. So what should we put here? And before.next and yep, before.next.next. This makes sense, right? This is a memory location. Before.next is equal to before.next.next. It doesn't, well, so it looks weird. But what we're saying is that basically the memory location of, okay, the memory location of before.next.next Okay, resolve this one. We're going to store it in before.next, in the pointer before.next. Right, which is why I have this little cutout over here so that I can say this is where we're storing the memory location. Okay, so we point it over here, and that just resolves that. Now, is this going to fail? Like, what about a null pointer exception? Well, no. It's not going to fail because we know that this is the index we're trying to remove, right? And the thing after it can be null, and there's no, and if I plus 1 is null, that's no problem. That just simply resolves to null right over there, and we store null. We make his next null. Yes?
Is this more efficient than the previous way, or?
It saves a variable, and it helps us get prepared for what we're going to do for the doubly linked list. So the idea here is that because one of the test questions I'll have is like I'll have nodes A, B, C, D in a row, and I'll ask you something along the lines of which node are we pointing to now after I do a.next.previous, previous moves you backwards, next, something. So I'll give you something like that and ask you which of the 4 nodes am I pointing to, or did I go out of bounds somewhere, right? So it's a pretty easy question to answer, but I mean, it also makes sure you understand that basically you're just moving around. It primes you to think about everything in the right way. Okay, so let's go ahead and test this, right? So we were adding to the head 5, -12, 0, 1. Let's go ahead and make sure we can add to the end. So -12, 0, 1, and then 5 got added to the end. Now let's go ahead and do list.remove 0. So that will remove the -12. And then let's go ahead and do list.remove the thing at index 1. So that will remove that 1 from the list. So this remove operation does work. So I didn't mess up when I'm programming. It is pretty obvious when these things don't work because of the way the print line works. The print line iterates through, it follows all the .next pointers. So if something doesn't get added or multiple items get removed, you'll know about it. Yes?
Should I still be pointing at the next one?
Okay, so what happens over here? That's fine, because what's going to happen to I? Or what's going to happen over here? Well, I doesn't have anything pointing to it, so it's going to get garbage collected, and it's not going to keep pointing to the next one, so it'll get deleted. So yeah, thank you for reminding me to finish that one up. All right, so that's singly linked list for you. So what you're going to be working on for your homework is that you'll be creating a doubly linked, sorry, not a doubly linked list, but a circular linked list. And the thing about that is that the head, there will be a head and a tail variable. So we're going to be keeping track of both the first and the last node. And the last node, instead of its .next being null, its .next will be head. So it allows you to wrap around. And you'll see that this has useful applications when we're trying to create like circular queues and stuff like that. But that's going to be your homework. But there's another type of linked list. This isn't typically how linked lists are done because this is a valid way to do linked lists. But disadvantage of the singly linked list that I implemented. First off, most of the time we do keep track of a tail variable, right? Okay. And I'm not going to implement it here just to save time. I'm going to implement it for the doubly linked list, which we're about to do. And if we use a tail variable, though, this means that we can add and remove items from the beginning or end of a linked list in constant time. But if we have to remove something from the middle or add something to the middle, that's going to take, if we have to use the getNode call, that's going to take linear time to do. So these things are very, very efficient for adding and removing stuff from the head and tail. Okay. Disadvantage of this is that the singly linked list is, unfortunately, we can only go in one direction, right? We can only iterate from the front to the back. Sometimes it's useful to back up, right, or to reverse it. And it would actually, to go through the list in reverse right now, it would actually take n squared time because you'd have to go all the way to the end. Then you'd have to go to n minus 1, then n minus 2, and then so on and so forth. So that'd be 1 operation plus 2 plus 3 all the way to n operations, which would be, so 1 plus 2 plus 3 all the way summed up to n. That's, you learned, is O of n squared operations. So instead, we'll go ahead and create a doubly linked list to deal with this. Doubly linked lists are more common. I believe that's the way Java implements their linked lists. So you can go through them forward and backwards. And they pretty much are. Oh, the nice thing about this is that we're going to be able to use a heck of a lot of the same stuff we used for this. So, but we'll go over and we'll write this first. So first we'll create double linked list. Doubly linked. I'll just call it double linked list. We'll create our main method. It's going to be in the same thing, and it's going to take in a variable of type E, right? So the primary difference with a singly linked list and a doubly linked list, it comes from our internal node class. So public static class node E. Okay. And what we're going to do here is that we are going to create a another node class. This node will be called, so it's going to have the same thing. We refer to the same name. It's going to have an E item, right? Just like the original did. So private E item. We're going to have a private node E next, right? And we're going to have, but the difference is that we have now a private E previous, which we'll just call pre for short. So not only do we keep track of the node in front of us, but we keep track of the node behind us. As a result, our linked lists get drawn, and I'm going to go for a much more simplified view just simply so I can show the arrows a bit better. Our linked lists are going to look something like this. So I'm keeping my arrows going to the next on the bottom and the ones going previous on the top, right? So, and this points to so this is the head of the list. Its previous is null, and the tail of the list, its next is null. So I'll be keeping track of the tail for this one too. Okay, just so that we can do this. Now, keeping track of the tail the reason I didn't want to introduce the tail earlier is that keeping track of the tail, it takes our add and remove method and takes it from the 3 conditions that we had to 5 conditions. Now, that sounds like a huge increase, but the hardest part about it is, again, the everything else category. The other ones are pretty easy once we know what they are. So let's go ahead and finish the constructor for this guy. So public class, so public node. This will take in an item. Cool. Okay, right? Going to take in an item, and it will be. So we'll say that this item is equal to the item you just passed into me. So we'll create a node we'll create our node like this. Okay. And then the other thing we're going to do is that it turns out that, that since like the toString method and the getNode method, they all work by just going in one direction. We'll just go ahead and copy paste. They work fine without having to use a next or a previous. So we'll just copy them over into here. Does that make sense? Since they're going to go in one direction anyway, the toString method and the getNode method we can just copy and paste into here. Okay, so the getNode and the toString method, that isn't going to change. Is that fine with everybody? Okay, so let's go ahead and set up our variables. So the first thing that this needs is a private node E head of the list, a private node E tail, and a private int size, right? The only thing that happened is I added a tail, which I wanted to do in this time, but I didn't because I wanted to make sure we had plenty of time, right? So no difference in the variables here. Let's create a constructor, public linked. So this is I called it double linked list, so double linked list. And we're not going to take anything in, so we're just going to set head is equal to tail is equal to null. Actually, we'll probably just split that up into multiple statements. Head is equal to null, tail is equal to null. and size is equal to 0. Okay. So that's our doubly linked list. So again, the only real differences are going to be in the add method and the remove method. So we'll just hop right into that. Now, with the doubly linked list, you might think that basically since we've got twice as many pointers to move around, it's going to be twice as hard to do. And you're wrong. It's not going to be twice as hard to do. It's going to be 12 times harder. No, I'm kidding. It's going to actually be much easier because while it's easier, while there's more stuff to move around, there's a lot more flexibility. You've got a lot more, because you can go backwards. You've got the opportunity to make less. It's there if you put one line in, you can say, oh well, I did this first, so I can do this instead, right? There's a bit more flexibility you have in solving the problems. So this makes it a bit easier, in my opinion. Or it's basically the same difficulty, in my opinion, as a result. So we'll go ahead and write public void add int index. So we're going to add an item int index, right? And again, all we're going to do is that we're going to overload this method. Public Boolean add some item over here, right, to the end of the list. And we'll just simply do the exact same thing, which is return true and add let's not add index. Add this item to index size, right? Add it onto the last thing in the list, right? So over here, let's go ahead and check off like the things that we know how to do already. So the first thing that we know is that when we create this, is that when we add something, definitely want to remember to increment the size. Otherwise, the get node function and our checks to see if they're out of bound, they may not work. The size, keeping track of it isn't going to kill you over here. It will kill you in the circular linked list. So make sure you keep track of the size. Then we have 5 conditions. So 3 of them are the same. So the first 3 conditions are the same, which is that what if we want to add something and it's out of bounds? So if index is less than 0 or index is greater than or equal to size. Throw new index out of bounds. Okay? Oh, exception. Okay? Then we had figured out 2 other conditions, right? If the index is equal to 0, that's adding the new head, right? And then we had an else condition for everything else. So new head, right? Everything else. So we have 2 more conditions we need to figure out to add. So, right, we also have a tail that we're keeping track of now, right? So it makes sense that basically probably the other condition is, what if we add in a tail? Right? Else if... So how do we know if we're adding a new tail? What should the index be equal to if we're adding a new tail? Size. Just size. And the last condition is, well, is just one that you might not think of, which is, what if we're adding the first thing in the list? If we're adding the very first thing in the list, we actually get into a very interesting state. Yes?
It's not size minus 1.
No, because because size minus 1, that's a index that already exists. Size minus 1 is already an index that exists, so we're adding on to the next possible index, which is size. Right? So that's a great question. Okay. So the other thing is that the last condition is actually that we think of is actually the first one I want to add, which is, what if we're adding the very first thing to this list? What if the list is completely null? Now the way I wrote my new head would have taken care of that originally. But the problem is that also that if it's the first thing in the list, right? If it's the first thing in a doubly linked list, then it's in the unique position. It's both the head and the tail of the list. That makes sense? The first item is both the head and the tail. So the last condition, or rather the first condition over here, is that if the size is equal to 0. Now notice that all these cases are mutually exclusive from one another, right? Only one of these can fire, right? Okay, so I don't have an else if over here, but if this statement execute, nothing else is going to execute, right? What just happened there? Do I have too many curly braces somewhere? Size plus, I do have too many curly braces somewhere, I think. So where? So time to search for that extra curly brace. Do everything. There we go. Back. Okay, now Control A. There we go. See, even I accidentally put in that missing curly brace sometimes. All right. So if the size is equal to 0, well, this one, let's go ahead and remember we needed to create, first off, we have to create a container for our item. So I see this in the exam a lot of times, by the way, where people forget that their node has to go inside, where the item has to go inside a node. These items don't have next pointers. A lot of people forget that. Node E item. There we go. So now if the size is equal to 0, meaning adding is going to be the very first thing added to the list, then it's going to be both the head and the tail of the list. So this dot head is equal to adding. This dot tail is equal to adding. We don't have to adjust his next or previous because they're both going to be null in this case. Okay, that makes sense to everybody. We don't even need to draw this one out. We're just creating a node, and it's both the head and the tail. All right, so now we've got to go through all these ones and just simply add all the other ones. So let's go ahead and start new tail. So let's go, new head. So if we're adding a new head to the list, all right, so we've got this new node over here, right, and we call it adding. Let this new node be adding. Right, let's think about how we did it with just with the singly linked list. What we did with the singly linked list was that we attached this guy over here, right? And then we just simply made this guy the head as well, right? That was the 2 steps that we had to do. We just need to do one more step, which is that we have to take this pointer and connect it over there. Does that make sense to everybody? So we have 3 steps to do. The first one is that we are going to attach. The same rule follows. We should attach whatever we're adding first. So the first thing we're going to do is that we're going to attach adding to the current head of the list. So adding dot next is equal to head. Okay, its previous is null. It should be null, so we're going to keep it that way. Okay, what about head? The current head of the list. Well, its previous should be equal to adding, right? So we say that this is the head, and this is the previous. So this is not. This is adding. We say that the previous pointer, which was formerly null, points to this guy over here. Okay. And the last thing we have to do is just make sure that we update what head actually is. Now that it's fully attached, we've got to make sure that we're keeping track of everything. So head is equal to adding, right? New tail works surprisingly in the same way. It's symmetrical. Okay. So let's go ahead and create this guy over here. This guy is currently the tail. This is adding now. So here's our head. Here's our tail. Here's adding. Okay. So the first thing we need to do is take this node and attach it, right? So we attach it by connecting the previous over here. So we're taking adding's previous and attaching it to tail. Then we're taking tail's dot next and attaching it to adding. That makes sense? We're just basically flipping it around because we're just adding it to the tail instead of the head. So adding dot previous is equal to tail. Tail dot next is the current tail next item. Well, it's now going to be this node that we're adding. And now that node we're adding, because it's the last thing in the list, should be the new tail of the list. All right. And this is the last part of it where of course, you might imagine that it becomes a bit fun to draw. and by fun I mean messy, which is that basically what if we want to add it to index I, right? So I'll go ahead and remove, so we've got I, we want to add to index I, we've got I plus 1, and then we've got I minus 1 over here, right? So what do we need to do to basically attach them if we want to add this node in? Okay, now we'll go ahead and do the same strategy as we did for a singly linked list, just so we can makes it easier to follow. Since we're working off of what we already used, we'll just go ahead and grab the node over here before, right? So first thing we want to do is attach this guy, right, to the linked list, right? He needs to be the new index at I, so he needs to sit between I plus I minus 1 and I, right? So we attach him to before.next, and we attach his previous to before. That makes sense to everybody? Okay, so everybody's following that. So let's go. So again, this will look very similar right over here up until we start messing with the previous. So node E before is equal to get node at index minus 1. So we get the node before the location we want to add at. Okay, and we say that adding dot next is equal to the node that comes after before, right? And then adding's previous node is going to be the node that is before it, right? So the node that comes after adding is going to be the node that's currently after before. And the node that's after previous is going to be before. So we've attached it, but you know, this doesn't do anything. If we iterate through the loop, it's still gonna, if we iterate through it, it's just gonna skip over adding because neither of these guys point to it. So now we've got a choice here, and neither is wrong. Okay? Do we want to change this pointer over here first, or do we want to change this pointer over here first? And there's no right way to do it. We're going to have to make one completely obtuse call in order for this to succeed. So do we want to move this thing first or this thing first? The top or the bottom first?
Bottom.
The bottom. Okay. So that we're going to move before.next pointer, right? That's so before's the node that comes after before. Well, that's pretty simple to figure out. That's adding, right? That one's straightforward. So let's go ahead and very quickly draw that. So, right, this became a bit of non-Euclidean right there for a second. Or sorry, non-planar. Ta-da! That's attached. So now we need to move this over here, which we have to figure out the way to reference that. Okay? So we can't use before to so we could use before to reference that, but that seems a bit obtuse. So we need to figure out, okay, a way to first reference this node over here, the node over here. Then we can figure out how to use this, reference this arrow. Okay? So it doesn't have a label, but this is the node closest to it. So let's go with adding. It's the node after adding, so it's adding.next. And what's the arrow we're adjusting? The previous. So it's the node that comes after adding, adding.next, and we're modifying his previous. Right? So what are we storing? And we're just storing adding in there. Adding.next.previous is equal to adding. Right? And that will update all the links. You can see why these might be like fun interview questions, because they require you, if you try to do them in your head, it's terrible. Notice that I'm not doing this in my head. I'm actively getting up in here and drawing. Okay? This is not your greatest tool. This is your greatest tool. Well, not the dry erase marker. That's really cool, but pen or pencil and then using something to actually write on it. Write down your problems and draw them. That really helps. So we had twice as many lines as we had to do, but it really wasn't too much worse. Okay? So let's go ahead and look at the remove method. Or actually, first off, let's make sure this works, right? So double link So let's go with a double linked list. L is equal to new double linked list of integer. Okay. There we got here, and now for int I is equal to 0. Yeah, this is the tedious part. Sorry, I is less than 5. I plus plus. So we're just going to add in. So we're just going to do l.add I, and then we're going to system.out.println this guy, and then we'll go ahead and add. We'll add something. Oh, exception, out of bounds exception in add at lines 17 and 24. So, and this was caused at 108, which was the add method. So 17, and then 24, which was that. It says it was if the index was greater than or equal to size. So I want greater than. Whoops. There we go. 0, 1, 2, 3, 4. Okay, so there was just simply my exception. Just I wrote down the exception wrong. So let's go ahead and try adding everything at index 0 instead. So it should go in reverse order now. And now let's go ahead and do l.add 100 at index 2. There we go. Semicolon. Okay, that seems to work. So now what about removing things? Because that seems like it's a bit harder. I mean, it's the same theory, which is that basically we don't really change this too much. Public e remove int index. So it's the same as doing the singly linked list, right? We're going to remove this item. We're going to have an item to return. Null. We're going to return the to return. Right? We're going to decrement the size. And then we have the same the 5 conditions we need to deal with, which is if index is less than 0, or if its index is greater than or equal to size. It's greater than or equal to here. Okay. Next is then we've got to figure out what the other 4 conditions are. So the first condition was the first of the new conditions was this, right? In the add method, it was what if the size is equal to 0, right? What if we're adding the very first thing to the new, what if we're adding the first thing to the list, in which case it has to be both the head and the tail. Well, here we need to think about what if we're removing the very last thing in the list, right? Because then we have to set both the head and the tail to null. So if the size of the linked list is equal to 1, then we need to remove the very last thing. Okay. Next, our condition is what if we're removing the head of the list, right? What if index we're removing is equal to 0? Otherwise, what if we're removing the tail of the list? So the tail is located at what index? Size minus 1. And then removing everything else. All right, so we've got our to return. So if the size, this first one's fairly easy, just like the size equals 0 was easy. We don't even need to draw it. If it's the last thing in the list, then we say that to return is equal to head.item, or we could put tail.item. Remember, we're dealing with the very last thing in the list or the very first thing in the list, so it's the same thing in this case. And then we set this dot head is equal to null, and this dot tail is equal to null. And then we're done, right? Okay, now we need to remove the head, and we need to remove the tail of a linked list, of this doubly linked list. Okay. head of the linked, so this is the head of the linked list. We need to remove it, which means that this guy needs to be head of the linked list. Okay? And the way he needs to get removed is that we need to make sure that nobody's pointing to him anymore. Right? So what we did in so we stored the item, right? That was the thing we did in the first so the original one was the following operations, right? In a singly linked list, we just simply did this. To return is equal to head.item, right? And then we would say, and then we said head is equal to the item that comes at head. The current head should be the item that comes after head, right? And what that's going to do over here is that's going to update this guy to being the head, right? But what it's not going to do is that this is not going to get rid of this node. If we go backwards, we're still going to hit this node because this arrow still exists. There's still something pointing to this. It's this previous thing. So we get rid of that by saying by getting rid of the pointer. So head.previous is equal to null. That makes sense to everybody? That will erase this arrow. Okay, and then this item will get garbage collected. So now let me redraw. What if we want to remove the tail of the linked list? Similar thing. What we're going to do is that we are going to say to return the item we want to save, if we're removing the tail, is the item in the tail. Tail, and then the item that what should be the new tail? Well, it should be the item that comes, it should be the node that comes before the tail, right? So actually that's tail is equal to tail dot previous, right? That makes sense. The item that comes, it's the node that comes before it. And now we need to do this pretty much the same thing, which is that this node is currently the tail, but this pointer still exists to this thing, so this still exists. So we've got to set tails.next equal to null. So it's kind of just it mirrors what's above it, right? Did this make sense to everybody? These removable operations? Did I go too quickly on these?
Yeah, can you repeat it again?
Sure. So for removing the head, what we had to do is that, right, in the singly linked list, that's all you need in a singly linked list, right? But because because these things are doubly linked now, they still have a pointer to the thing that we're trying to remove. And if we don't get rid of that pointer, that thing is still going to exist. So we have to remove we remove the pointer, we set that memory location equal to null, and as a result, the garbage collector will now collect those old items. Does that make sense? Did that help explain it?
Yeah.
Okay. All right, so now we need to remove an item from a doubly linked list. Okay? Or any item from the doubly linked list. Okay? So let me go ahead and redraw this a bit nicer. We need to remove the item at index I. Right? So here's I minus 1, I plus 1. Right? And we're going to just keep this simple. We're going to mirror everything we've done previously, which is that we're going to get this guy as before, as the node before, and that's the only reference that we need, right? So what we need to do, so again, what do we need to do to get rid of this item over here? We got to make sure that there's no arrows pointing to him. There's nobody's keeping a reference of this guy to remove him. So how do we do that? So which are the arrows that are referencing him? This one, the 4.next is referencing him, and then this thing over here is referencing him, which that'll be an interesting thing to get to. I mean, assuming it's not null, right? Because this thing could very well be null. So how do we do this? So, well, first off, actually, that's not something we have to worry about. We know that this item, so first off, we know that this won't be null. How do we know this?
It's not the last item.
So the item we're removing is not the last item in the list, right? That was a condition, right? I told you the way I programmed this is very specific. It helps us protect ourselves from basically these kinds of situations. So we know that there's an item after here. So we know that we can access this node over here, right? We know we're in this configuration, that we're trying to remove this item. We know there's something before it and something after it. Because otherwise, if there weren't something before and after it, we would have been in the other conditions. Okay? So the first thing we need to do is store the value stored in here. So to return is equal to the, so let's get to that node that comes after before. The node that comes after before, which is the node we're trying to remove, dot item, right? For.next.item. Oh, and I need to actually get the node before. So node E before is equal to get node at index -1, right? So now I have to remove this before.next pointer. But before I do that, if I get rid of this arrow first, I really have no way to reference. Well, actually, yeah, I do have a way to reference that. Okay, so just keep in mind what we're gonna do here. So the first thing is let's go ahead and get rid of the before.next, because that will make it easier than trying to reference this long thing over here. Okay, so before.next should, instead of pointing to this guy, we need to point to this guy, right? Which is the same call as we did before, which was before.next. So the node that comes after before should be the node that's 2 moves away from before, right? So, right, the node that comes after me should be the node that's 2 after me currently. Okay, so now this takes effect. This updates to this operation. So now we can actually access this node pretty easily, because it's now this node is currently our before.next. So now we have to adjust this pointer. Now if we're using the vantage point of before, this node over here is the node that comes after before. So it's before.next, and its pointer is .previous. So we say, so we want to change before.next.previous. Right? And this is why it's important to draw it out, because otherwise this wouldn't make any sense whatsoever. Before.next.previous pointer, it needs to point to this node, which is before. Well, assuming I can spell it. All right, and that will successfully remove it. Because again, what we've got over here is this over here. Nobody's pointing to this node anymore. It's going to get garbage collected. So that's the remove operation. Okay. So let's go ahead and test it out. So let's go ahead and we know that the adding works. So let's go ahead and do L.remove the item at index 2. And that removed the 100 I just inserted. So remove L.remove the 0th item, and remove the item at index 4 instead, which would be the last item. So this method, the remove method, seems to work just fine. Yes?
And the singly linked list, did anything point to that head so it wouldn't be deleted?
The head always points to head. Head always points to head, and tail always points to tail. That's how we're keeping track of them, to make sure that they don't get garbage collected, and so that we can access them. So that's a doubly linked list and a single linked list. So let's go ahead and do a big O analysis of these, right? But it shouldn't surprise you because it's going to be the same as a singly linked list, right? Adding. So if we were adding something to so if it was out of bounds, that took constant time to check that. If we're adding a new head to this linked list, that was 2 lines of code. Well, sorry, adding the very first thing, 2 lines of code, that takes a constant operation. Adding a new head, 3 lines of code, constant time operation. Same with the tail. That's 3 lines of code over there. Adding anywhere else, we have to iterate to that position using the getNode function, which means this takes potentially O of n time. Okay, and if we change getNode so that we can start from the front or the back, depending on what index we're searching it and based on the size of the list, then you're still going to iterate over half the items in the list, which is still a linear relationship. So it's still going to take O of n time. And the remove works exactly the same, where basically if we remove anywhere, if we remove the head or if we remove the tail, it's going to be a constant time operation because we're just manipulating these memory locations around. If, on the other hand, we're removing something from the center of the list, then we're in trouble because we need to do a linear time operation to find it. Okay, and we do need to do a linear time operation to find it and get there. Which brings us to the disadvantage of the linked list again. We didn't program get and set over here, but I'll just simply show you get over here just to, and I'll leave set to you. It's not really too exciting, but private static class. Yeah, you can look up what that means, but basically means it's just an internal class. So public get int index. So this gets you the item stored in an index. So the first thing we have to do is get node node is equal to this dot get node at that index, right? We have to iterate to that node, and then we have to return node.item, right? So the get node requires us to, get requires us to use the get node, and set would require us to use the get node function. That makes sense to everybody? We have to, if we're getting something at a random index inside the list, we're going to have to iterate all the way through the list to find it until we get to that appropriate thing. So that brings us to a good discussion of what I mentioned on our exam is going to be worth 20 points. Okay, which is let's compare and contrast linked lists to array lists. Okay. So first off, there's basically 4 operations we care about, right? There's add, remove, get, and set. And pretty much there's other operations like checking to see if it has something. Yeah?
For the single linked list, you could technically have a tail on it.
Yeah, I just didn't. Singly linked lists have tails. I said it was an exercise left as an exercise to you because you're going to be programming something very much like that for your lab. Okay. So add and remove, right? Add and remove, they're always they're symmetrical, right? So add and remove we can group together. So the add and remove operations we can group together. And same with get and set, we can group those together, right? Okay, get and set. So I'll put AL for array lists. And you'll have to put in a bit more information than I put in here. I'm just going to summarize the information that I say in this table. And linked list on that side. Okay? Yes?
The test, will it be like a open-ended question? Like
yes.
This? Okay.
It'll be a pretty open-ended question, but I will give you some direction. Okay? So add and remove functions for the array list. Okay? Let's think about the array list. So how long does it take to add stuff to an array list? And this is actually possibly the toughest of these 4. Yes?
It's over 1 unless you have to resize.
Is it? Oh, is it constant time to add something? What if I'm adding something at the beginning of an array list?
Then you have to shift.
Then I have to shift stuff over. So it's actually, let's think about the cases where, so what cases will I have to shift stuff over? Right, that's the big cost in an array. So array lists, right, they have 2 potential costs then. The first potential cost is that we have to shift stuff over. And the second, as you mentioned, is that we have to reallocate, right? So if we shift stuff over an array list, that's going to be O of n. If we have to reallocate stuff, it's going to be O of n. What's the only time we're not going to shift stuff over? If it's at the end. So All the other times, it's O of n time because we have to shift. And that's because if we add or remove an item, we have to shift stuff over. Okay. The exception to the rule is the end. Okay. If we're adding or removing something from the end, that's an exception there. If we're removing from the end of the list, it's going to be constant time operation, right? So, okay. But that happens pretty rarely. If we're adding something to the end, that's going to be a constant time operation, except for what case? Where we have to reallocate, right? So you'll need to put more than what I put here, right? But I'm just simply summarizing all the stuff I said. Okay. Okay. What about adding or removing from a linked list? We just went over that. So what's that? Where are linked lists good at adding or removing? But where? They're constant time where?
Head or tail.
Yep, head or tail. And you raise your hand in the back. Where are they bad at adding?
Anywhere else.
Yep. Why, by the way? Because for the heads and tail, it makes sense because we have access to head or tail. But yeah,
You have to go through the list.
Yep.
Find the node.
Yep, because you have to iterate. Okay. So let's look at getting and setting stuff. So remember, this getting is where we get a value from a specific index, and setting is where we swap out a value at a specific index. So what about array lists? Are array lists good at that? Yeah, I see nods here. How good are they? Sorry? Constant time. Right? Because they're built off arrays, and arrays, if you're just getting a random index, that's a memory location you can look up. Right? Otherwise, you can set it up. Okay, what about for a linked list? Getting and setting at a random location.
O of n.
Yep, they're O of n. They're terrible in comparison. They're sluggish. Unless, of course, you're getting the head or the tail, which you have a memory location to. But if you're looking for anything in the list, you have to iterate to that point, right? Okay. So that would be it, except there's one more thing we have to just look at because we were talking all about time complexity over here, right? These are all about time, but there's one other dimension we have to work with, which is space, right? Right? It makes us sound like we're talking about stuff from the Avengers when we're talking about this, but you know, but no, we have to think about the space complexity as well, okay? Which is basically how do these things use up space? Okay. All right. So how do array lists use up space, and can they waste space at all?
Yes.
Yes. So how do they use up space? Anyone? Yeah.
One doubles the array.
Yep. It doubles the so array lists will double. Doubles when needed. Okay. And how does this possibly waste space? Yeah, there's space that you might not be using. Yeah, you can doubles when needed, but you might not need double, right? You might add in your capacity might be 500,000, right? And your capacity might be 500,000, and then you add that 500,000 in first item, right, to there, and so the capacity doubles to 1,000,000, and now you're wasting pretty much 500,000 spaces, even though you just needed one more item. So that's the thing there. You might be using up a bunch of extra space. So linked lists require you to think in a different way about how they might be using up space, though, right? Because you're not creating extra nodes you don't need. But what space is being used up? What extra space is being used up by our linked lists?
Just the one node you're adding?
Not necessarily. What? Sorry? None? There's extra space being used up when you compare it to an array list. Yes?
Memory location?
We have to keep track of these memory locations. This comes at a cost, right? Every item, okay, first off, this isn't actually the item being stored in there. This is a memory location to that item, right? This is the memory location of that item where we can find it. So we're storing that memory location. And that's how array lists work, by the way. An array list of objects, it doesn't store those objects, it stores the locations of the objects. But nodes have that additional overhead where they're storing the memory location of the thing the thing after it, and the thing before it, right? So basically for every item you're storing, you're using up, this is 4 bytes, this is 4 bytes, this is 4 bytes. So you're using up an additional 12 bytes per an item, which doesn't sound like much until you're using up until your list a million items and you're using an additional 12 megabytes, which doesn't sound like too much these days because it's not. However, billions of items, that's an additional 12 gigabytes. So there is a cost associated with the linked list, and that is the memory locations there, right? Does that make sense? The memory locations use up some space. Yes?
But that's still better than array list.
In the array, not necessarily. If the array list is the exact size you need it, right? Then you're using, let's see, three times as much space for a doubly linked list, or twice as much space if you're using a singly linked list. Because an array list, they only keep track of the memory location of the item, right? So this one, there's no clear winner here. But right? So there's not really a clear winner unless you know exactly how much space you need, in which case you want to use an array list. But if you know exactly how much space you need, you might as well use an array. So array lists there's some people have a deep-seated hatred for array lists. But, I find them useful for doing this comparison and contrast. It also brings up the point that there's multiple ways to implement these data structures. Okay? Now, so this is most of chapter 4. This is most of chapter 2 right here, right? So let's go ahead and look at the last thing in chapter 2 just for completeness sake, which is not something I'll code up, but something you should probably know about, because I've actually coded it up for the lab so you don't have to write it yourself. And that is the iterator. Okay, so documents. No, that's downloads, documents. There we go, Kaufman. And there we go. Sorry, give me 1 second. So, right, for the slides, we didn't really need a lot of the slides because they went, right? So they go in what if we want to make these lists, right? So they mentioned that basically they've created, so let's go ahead and see. There we go. The linked list class and the iterator, listator, and iterable interfaces, which sounds like a lot, but this is not stuff that's going to be on your exam. It is, however, on your homework and mostly there for you to figure out, and you kind of just silently use these iterable and iterator stuff a lot of times when you use the for each loop. So we've done the linked list class. This is that's cool. The iterator is kind of that the current and then current.next thing, except it's built into the class. You can view it as basically a moving marker that keeps track of where you are on a linked list, going forward and backs. It starts at the first node, and then you can ask for the iterator by using the .iterator method. Okay, so if you use the actual linked list class, you can get an iterator by calling the .iterator method. And then you can advance the iterator by calling the .next, and it traverses it will basically go through your list basically one item at a time. So it helps you traverse the list. And basically, these are the 3 methods that an iterator needs to have to be considered an iterator. Is there something after me? Right? Is there, if I'm going through this list one item at a time, right, one node at a time, is there an item after me? And if there is, then I probably want to go to the next item, right? And then the ability to remove an item from the list, which is pretty useful. The iterator is conceptually between elements. It doesn't refer to any particular object at any given time, right? It goes and advances and gets items and then backs up, but it will remove items. And you'll want to look at this in more detail on the code I give you, because because if you use the iterator I wrote for you, you don't have to write one. Use the iterator I wrote for you, and the Josephus problem that I assign you will become trivial. Okay. So basically, the idea here is that you can use an list iterator that will also be able to. It basically has a bunch of other methods. It allows it to go back and also add items into a list. So basically, it's a way to manipulate a list. So these are pretty cool, just little classes. But the reason I bring them up is that for the enhanced for statement, or as I've been calling it, the for each statement, and that's the one where basically, right, it's the right. So if we've got a list, we call lowercase list, right? So we could go through it like for e item in list, right? Everybody remember this for loop over here? This type of for loop? What this does is that it creates an iterator to go through it. Okay, and that's how this works. It creates an iterator, and so long as it uses the has next and next to automatically advance for you. So this thing automatically uses an iterator for you and automatically goes through stuff. Okay, that makes sense? So that's how that for each method works, and why you can only use it on certain things and you can't use it on other things. Okay. So going through, so you'll get more experience with those working with the homework. I just wanted to let you know that that was something that you should do. And the last thing is that basically this is kind of where we are in the whole thing, series of things. So we learned about the list over here, and all these lists are type of collections, which is basically it's exactly what it sounds like. It's a collection of data. It's a way to organize data. So we've learned about the list interface, and there's a whole bunch of other, and we learned about specifically how to do array lists and linked lists. Next on the next 2 chapters, one of which we'll probably get through tonight, after our break, is the stack. And then we'll go on, and then when we get back next week, we'll go over the queue. And then once we're done there, we're going to learn about, and it's not up here because I don't think Java implements them, but we'll learn trees after that, and then we do sets. But basically, we learn a lot of the bottom boxes in this table. We'll learn about hash sets, tree sets, and then maybe we'll learn about these skip lists. But the idea here is that the reason we get this weird Boolean add method, right, why we have 2 methods, is because all the things in Java that are collections, they have that single add method, which adds an object, and it doesn't care where it adds it at, right? So that's why we have that Boolean add method. All right, so let's go ahead and take our quiz for the evening, okay? So, and we are done with chapter 2. So, assuming that everything goes as planned, we should hopefully be taking the exam next week on Thursday, but depending on how crazy things are with, Thursday not actually existing this week, we'll see if we push it back. If we push it back, I'll probably move some content about stacks into that exam, okay? So I might move some of chapter 3 into there, okay? So, and give me opinions, by the way, because we've just covered everything that's going to be on the exam pretty much tonight and the past couple lectures. So so this is the linked list quiz. Yes. Stacks.
Are they on the first two?
They will be if we have to delay it. So your password is the first 4 digits of pi, which should be 3141. Okay, so I'm going to go ahead and minimize this, and then I will